Okay. Okay. So, right. So we have seen so far about machine learning. Okay, I've covered the basics of machine learning, supervised. Unsupervised, you have a very strong algorithm called k-means clustering, which actually people confuse it with k nearest neighbor. It actually has a similarity, but there is one difference. It does not have a label, and it actually uses what is called centroid mechanism actually in calculating. The same distance mechanism is used, and they calculate the centroid, and they try to find, first they randomly put a centroid, calculate the distance, then they keep on moving the centroid to find the optimal position when it has reached, and that is how the k-means cluster. So that is used, as I said, for unlabeled data for grouping and clustering and features classifications and things. Right. Now, so now we'll go into the world of deep learning. Okay. The basis of deep learning actually starts with neural network. Now, machine learning, deep learning. Now, deep learning is also a part of machine learning only. No, it's not very different. But they actually put deep learning as a very big thing where there are lots and lots of work that is actually being done and can be done. So are we going to say machine learning cannot be used? The traditional algorithm, no, those are also used, but deep learning gives you actually like very higher accuracy. There are lots of complexity actually can increase that can actually try to give you a very good prediction model compared to the traditional machine learning. So that's why the current trend is actually going more towards deep learning based model. Even for NLP kind of a thing, previously we never thought about using like deep learning, but today with a natural language processing and thing, deep learning has been integrated with NLP. There are some models called the BERT model, transformer and thing, which actually I recently attended an FTP from Samsung Research. They were talking about like the BERT model and thing, and I'm also doing actually a project with Samsung on a thing, Samsung project actually with R&D Bangalore regarding actually what is called like deep learning for intent classifications and things like that. So that is how deep learning has started to make its way in lots and lots of applications today. You can actually say lots of applications where deep learning has a predominant applications actually. Okay, so where did it all start from? Neural. So neural network, if you look at it, most of us would have learned science, biology and things. It actually comes from the concept of your human brain. The human brain, the skull, actually, if you take it, it is actually made up of lots of neurons. So neurons are actually like complex networks actually. So when we are doing certain thing, how exactly are we doing it? Let's say someone is talking something, you want to respond. So why do you respond? How is your thing that is making you to respond? So the input that actually comes to you is heard by you, the person talking. That input actually goes all the way to the neurons. It will activate the particular neuron, and based on the activation, you give the appropriate output. That is what is a neural network is. So this technology of neural network in the computer is actually borrowed from the biological neuron of the human brain. Actually, it has been taken. So a similar concept is actually used in artificial neural network also, wherein it has what is called an input layer. Because if you look at the neuron structure inside a human brain, it's very complex actually. It's very hard to know what is exactly happening inside, because I'm talking something, you are telling something. So say something that is happening inside the human brain. I really don't know what is exactly. That's why I say it's like a black box. So what is happening inside my skull? I don't know what is happening. So based on the input, I'm doing some action, right? Because the neurons are getting a similar thing is what's happening in artificial neural also. It has what is called an input layer. Then it has what is called a hidden layer, and then it has what is called an output layer. So this process is referred to as what is called a feature hierarchy. That is, you actually try to feature the data, okay, classify the data and things. And each of the layers here actually has a specific function to do, where it performs some specific work like sorting, ordering, and things like that. Now this neural actually can actually do both supervised and unsupervised learning, both for labeled and unlabeled data. this artificial neural actually can be used. So some of the rudimentary things that you have to know when you're working on neural network is the perceptron. So what exactly is a perceptron? A perceptron is nothing but a single layer neural network, meaning it has an input, it has an output layer. That's all it has. So what will happen here is there are no hidden layers or anything here. The input, if you look at it here, this input which is connecting to the output neuron, they will have a weight associated with it. So this weight will be multiplied by the input value of the input neuron. Then this input, the second input that is coming, there also there will be weight associated with it. So that weight also will be multiplied by the input neuron, and accordingly an output will be produced. That output could be in the form of numbers, it can be in the form of images, it can be in the form of discrete values, it could be anything else, or it can be linear value, whatever it is actually. So that is what is actually used for classification purpose or prediction purpose or some other things actually. The initial model of neural is what is called as a feed-forward neural network. Feed-forward meaning the data is actually going to be fed in the forward direction. There is no backward processing or anything. So the data, the input data that you are giving is actually going to go to the next layer, process the data and give the output. That is called as a feed-forward neural network. Okay, so here the perceptrons which I talked about, this is the perceptrons, remember, these perceptrons are going to be arranged in the form of a layers. So very simple example here. So what we are seeing here is the perceptrons are arranged in the form of a layer. So you have the input, then you have the hidden layers, then the output layer. Okay, that's what it is. So the output actually can have multiple neurons also. If you're going to have what is called a multiple outputs, or if you're going to have only two, you'll have two actually. Similar like that, here what will happen is each of the input neurons will be connected to all the hidden layers. So the weights here of the input will be multiplied, and accordingly the output will be calculated for the hidden layer. Similarly, the input here and this input here will be connected to this neuron. So the weight here will be multiplied, and then the output of that hidden layer actually is computed. Similarly, if we're connecting those things to output, again, there also the weight will multiply and we get the output. So what exactly is this hidden layer? Now, hidden layer is something like that is the black box, you can say. That is where all the computation and everything is actually going to happen inside. This has no interaction with the outside world. Because you have the input, you know what is happening. Output, you know what's going to get it. But in between, what is the computation happening is not known to the outside world. What exactly is the processing happening, how the outputs are actually given, nothing is actually, and this has no interaction with the outside world actually. These nodes are also sometimes called as a fully connected layer, they say. Fully connected layer actually. So this is the original neural network that was developed way back actually, called the feed-forward neural network, wherein you actually compute based on the weights, the sum, and produces the output, and you'll be connecting to the different hidden layers, the neurons in the hidden layers, and obviously you will get what is called the output. There is no concept of backward passing or going backward to do any kinds of corrections or trying to reduce the errors of it. Why I am saying is because the next thing we are going to see is the back propagation overall. Now, in the initial days, the feed-forward neural was effective and efficient, but there was no system or nothing that existed wherein you can actually try to update the weight or try to reduce the gradient loss or reduce the error that you are actually getting. But every system that you are producing, let it be even your machine learning, obviously there will be some errors that will be generated. Now you will always try to do some more iterations in order to reduce the error. The initial neural network that they developed did not have any kind of such system. So they brought what is called the back propagation, because the weights you initially assign could be a random weight. Okay. But as you get the output at each and every layer and you get the final, you will try to update the weights based on the error in order to improve the accuracy and reduce the gradient loss. So that is what we say in neurons, like how many epochs actually you run the neural networks. So you can run it like say 10,000 epochs and that actually can run even in batch level. Rather than giving all the data one at a time, you can also do it as like batch wise also. So that's why they say like, there is something called optimization here, where they use what is called like gradient, stochastic gradient, then batch level. So batch by batch also, you can give the data, train the neural network using backpropagation. So there are various methods by which you can optimize the neural network. Yeah, so there's proper tuning. So once you computed for one full epoch, actually, you can actually backpropagate it and you can go backwards, trying to adjust the weight based on the errors at the hidden layer, then at the input layer, and things like that. So you can keep on doing it with n number of epochs till you come to a point where you have reached the value what you have expected. That means the optimized model level has been reached actually. So that is what is a back propagation. So what you do is the weight of the input, that is for this one hidden layer, plus the weight of this one connected to this one, plus the bias will actually be taken to get the output actually. Similarly for this one. Then you actually do it for this output and this output. Then what you do, you try to back propagate it. So for back propagation, which is the traditional learning algorithm for training the neural network, they use what is called a partial derivative. A typical differential equation actually is being used in order to reduce the error at each and every level. That is from output to the hidden layer they do, then from hidden layer to the input they actually do in order to update the weight and reduce the error. So again, they actually do the feed forward with the updated weight and see how much you've got. If your error has reduced, then you again try to do the back propagation. So this one, they keep on doing it for n number of epochs till they receive an optimized model action. Now, as I said, in a human brain, when the neurons get fired, only you get the output. Yes, you are multiplying the weights, you're adding it with the bias, and you're getting the output. But for the neuron, actually in that layer, that hidden layer output, for you to get the output based on the sum that you have computed based on the weights, you have to apply some firing. That firing is actually done by means of what is called an activation function in the neural network. Activation function, what it does is the output that you get will be a what is called a real number or a whole number kind of a thing. Now this activation function tries to normalize that value. Based on that only the neuron is actually getting activated to produce output. Normalize the value between either 0 to 1 or -1 to +1 actually. So these modern neural networks, of course, as I said before, they actually train it using what is called a back propagation method actually. Now in the earlier days, they were using what is called linear activation functions, where they still use it. This one was actually used for the artificial neural called binary activation, wherein it will actually look for a threshold value. So based on the threshold, it will only give two values, either 0 or actually the 1. That is called as a binary activation. This one is a linear activation. It's still used actually. It's actually used in output layer. This is predominantly used for problems like, as I said, similar. This is nothing but like a linear regression of it, nothing else other than that. Wherein it is actually used for continuous value. For any kind of forecasting problem or thing, linear regression or a linear activation function is actually applied at the output layer actually. So it actually will give you multiple outputs, not 0 or 1, not continuous, not discrete values, but it will give multiple values actually. So that is where linear activation function is used actually. Non-linear activation have come into phase with the advent of deep learning and very complex data sets. Like for example, like even textual data, you can have complexity, images, video, audio. These are all non-linear data sets, wherein this kind of linear activation or binary activation does not hold good. It will not be very effective at all. So they also use back propagation. Of course, they use like what is called a partial derivative. Based on that, you actually make the computation for reducing the gradient loss and things like that. So in nonlinear activation, there are a couple of activation methods which I'm going to talk. One is sigmoid. A sigmoid actually follows a mathematical model which is like logistic regression, 1 by 1 plus e to the power of -x. Here, the values are actually going to be discrete value because only based on the probability of occurrence, you actually say whether the value is 0 or 1. So you normalize the output of the neuron anywhere between 0 and 1. So for x above 2 or below -2, you tend to bring the value of y axis in the range of 0 to 1 axis. And it follows this particular equation. Now, one of the challenge that sigmoid activation function has is something called vanishing gradient. Like how we had underfitting and overfitting in machine learning, we have something called a vanishing and an exploding gradient. What is vanishing gradient is, okay, let's take this one here. Now, I'm actually computing the what is called the output of this particular neuron and output of this particular neuron, right? I'm multiplying by the weights of the input I1 and also I2, and with the bias I'm getting it. Again, I'm going to do it with this one again. While back propagating, you will try to reduce the error by updating the bits. Sometimes, when you apply the sigmoid, because it's an exponential function, it actually tends to reduce the error so fast that it might tend to a problem wherein the gradient loss or the error will actually go near a value very, very close to 0, that the neural will stop working actually. That is called as a vanishing gradient. Meaning the gradient loss will actually get vanished. Okay, that is called vanishing gradient. And there is something called exploding gradient. Exploding gradient is something like where the weights actually get updated, like the values become too large. You will actually see a very large value in the updation of the weights. So that is what is called as an exploding gradient. So that's why one of the challenge they have when they apply sigmoid is it could lead into a problem of what is called the vanishing gradient problem. So that's why they actually go into this is the output of the sigmoid activation, very similar to a logistic regression only. So that's why they go for other activation functions like tan H, then rectified linear. Now tan H is something where it takes into account even the negative values, because in linear, or let us say even in sigmoid, it actually normalizes the value only between 0 and 1. Okay, so anywhere where the value is like, say, that is what they said. Like if you look at here, where the value of x is above 2 or below -2, they tend to bring the value of y anywhere between 0. That is what we compute the probability, because probability can never be a negative value. So that's why based on the probability of occurrence, they actually give a value which is 0 or 1. So that's why they actually go for what is called, that is the curve which you see here actually. If you look at it, this is the probability values actually. Anything below 0.5, that is actually given as 0. Anything above 0.5 to 1, the output is actually a 1 actually. So that is based on the values of x, which is -5 to +5. You try to normalize it based on the probability value between 0 and 1 actually. Right now, yeah. So in tan H, what they do is they actually try to bring in the negative values, the -1 to +1 actually. So it follows what is called a hyperbolic tangent value, where it actually differentiates between two classes, that is positive as well as the negative quantity also. So the concept of vanishing gradient, I think, is somewhat avoided in tan H. Then is rectified linear, ReLU. This one is a very, very important activation, which is predominantly used in most of the deep learning algorithms, CNNs and things. And the hidden layer normally applies ReLU only. Why they use ReLU is because ReLU avoids the problem of vanishing gradient, and it does not actually activate all the neurons at the same time. It actually goes very smoothly. It tries to learn very slow. At the same time, it is not like an exponential model. So it does not lead into the vanishing gradient problem actually. That's why they actually go to ReLU. So the initial ReLU actually they said is a function of 0, z. That means anywhere the value is negative, it will change all the value to 0. Where the value is actually, the output value y is actually like more than 0, you will have the value at z actually. So this had a problem because converting all the negative values to 0 is not a very good mechanism actually. So they actually brought what is called dying or leaky ReLU, wherein they introduced a small non-parametric constant called alpha, which is a non-zero value, and put a value called 0.01, which is a default value actually. So there they actually said like values less than 0, you are actually going to multiply by the alpha value, which is alpha into z. and the value which is greater than 0, it will be 0. So it will be max of 0.0 or alpha z comma z rather than 0 comma z. Then was softmax. Softmax is an extension of sigmoid only, wherein that we just calculate the probability of each and every occurrences. But along with the probability, computed probability each and every occurrences, it also computes what is called the sum of all probability also. So you compute the probability of the occurrence divided by the sum of all the probabilities it takes. So which activation function should I use for my work? So there is no hard and soft rule that this is the activation function you have to use. But mostly for deep learning and non-linear thing, you can actually try different activation functions. So only by trial and error you can find. But the rule of thumb actually says that the hidden layer normally you can apply things like ReLU or tanh, and the output layer you apply predominantly sigmoid or softmax. Unless it's not a linear data, you can apply sigmoid or a soft. But you always have to try different activation to come to a final judgment. But this is the rule of thumb actually they say. Now, so that's actually the precursor before the deep learning we had, right? Wherein even in neural, we have one single hidden layer, which we call as a multi-layer perceptron. Because the one without hidden layer is called a single layer perceptron. Deep learning is something like they allow multi-layer processing, wherein the layers are actually going to be stacked in hierarchical fashion actually. So there will be several pre-training that is going to happen within each and every hidden layer before you are actually going to get an output, and predominantly used in very big data level processing at the cloud and thing. This deep learning has its very good applications actually. So one of the model of deep learning is the deep neural network, which is nothing but an extension of an artificial neural network where there are going to be multiple hidden layers, meaning if you're going to have more than one hidden layer, say 2, 3, 4, sometimes you can have even 4 or 5 hidden layers. Obviously, it says that it is a part of deep learning called the deep neural network. So wherein it actually tries to find the correct mathematical manipulation to turn the input into an output. Of course, here also you're actually going to apply the same back propagation to train the neural network and apply the appropriate activation function where you'll be applying like ReLU or tanh in the middle and get the output where you'll apply either sigmoid or softmax. So you can see how clumsy or how complicated this network is. So this is how exactly each and every input are going to be connected to the neurons the hidden, and these things are going to be connected to the neurons the next hidden layer, and this one going to be connected to the next neuron hidden layer. To find out how many neurons you should have the hidden layer, they actually have a rule of thumb like 2 times the input or those kind of computations actually they actually use. So those many number of neurons you can have in each and every hidden layer, which is based on 2 times the input or n by 2 or the half of the input. There are various methodologies they actually use it. Okay. So this is exactly the deep neural network. Then is convolution neural. Now the data you actually give in the deep neural predominantly is always like only like numerical type of a data. Okay, or categorical data and things like that. But when we come to convolution, the deep convolution neural network, which is a part of deep learning, are actually going to give image as an input. So when you are going to give image as an input, think about it. You're going to give an image here like this one, like a vehicle. How do you expect that system is actually going to learn and classify whether the vehicle is a car, truck, or a van? So you as a human being, you exactly know this is a car, this is a van, this is a truck. Whereas the system does not know that one. So in deep convolution, there are various phases that it actually goes through before it is actually given as a vector to a fully connected layer to produce the output. So first thing what we do is the image is always in the form of RGB, meaning red, green, and blue, RGB format, the form of pixels. So that pixel values are actually taken and represented in the form of a grid or a matrix fashion we access. Then in this layer, there's a convolution layer. That's why it's called the word convoluting. Actually, you actually convolute the particular layer. You actually apply a filter. So there are various types of filters you can apply. So those types of filters are based on the different CNN models we actually have. There are things like AlexNet, there are things like BGG, there are things like Inception, and in Inception there are 3 versions like version 1, version 2, version 3, then Exception, ResNet, a lot of. Each of these convolution models actually use different types of filters. They initially started with the 11 cross 11 filter, which is a huge one. Then they reduced it to 5 cross 5, which was used in actually like AlexNet and thing. Then VGG actually used 3 cross 3, and then some actually use 5 cross 5 and then 3 cross 3. That is, they use 5 cross 5 in the initial convolution. When it goes to the pooling, they actually use a 3 cross 3. Then they came up with using like a 3 cross 3 filters and using 2 cross 2 in the pooling layer and things. So what exactly they do, if you ask, that matrix that I have, I will actually apply this filter. That is a filter that I'm going to take a 3 cross 3. I will actually stride it. That is, I'm going to pass it over the particular matrix where I have the image represented in the form of a matrix fraction, which is an RGB pixel numbers. So when I'm actually going to pass the filter over the particular matrix, I will say it's a stride of 1. Stride of 1 meaning I'm going to actually make the computation for actually 1 pixel at a time. You can actually also do like 2 pixels at a time also. So it is up to you, like how you're going to apply the filter. Is it stride 1 or stride 2? So it's a very technical way to say like it's a stride 1 or stride 2. So you're going to actually compute 1 pixel at a time or 2 pixels at a time. So when you apply that filter, which is a 3 cross 3 or 5 cross 5, so those particular values, the 3 cross 3 values are taken from that particular matrix of the image, and you apply a dot product. And after you apply the dot product, apply the ReLU activation to get the corresponding output. So the output you get, you actually try to normalize it between max of 0, z. That is like alpha z, z actually. Try to normalize the value because you might get even negative values and things. So you'll actually have to normalize the value and produce. Then again, you apply the pooling where you apply a 2 cross 2 filter. So you will take those 2 cross 2 matrices actually. Try to take the maximum value out of it. In pooling, there are 2 methods, max and average pooling. Predominantly, people go for max pooling. Again, you do the convolution of the matrix thing, whatever you have achieved, apply the filter, then do the pooling. So there are models which actually has like 20 convolution layer, 10 convolution layers and things. And finally, once you have access, so there are things where you use even like 3 cross 3 and a 2 cross 2 at the pooling. Sometimes they even actually apply the like 3 cross 3 and then pass it through a 1 cross 1 filter. That is for dimensionality reduction, because you try to reduce the filter size. So you actually try to maintain the quality so that the computation efficiency is also improved actually. So that you do. And finally, you reach to this point where you have actually flattened. Flattened means the complete matrix value will be flattened as a one single vector. And that is then passed to what is called a fully connected layer. That is nothing but a typical feed-forward neural network, nothing but other than that. And where you apply what is called the softmax, that is an activation function to produce the output, which will actually say whether the image is a car, truck, or van. So how they are actually converting is a pixel is when you look at an image, they actually take into things like edges and things like that. For each and every pixel, they are actually trying to compute what is the pixel values and things. That is how they are represented. So each of those values represents the edges and things in the image. And accordingly, only if there is that is why, like if there are any kind of cracks or anything, those things are accordingly given the pixel values. So based on that, only calculation is done. So now once you've trained a model, so now when you're going to give a new image, the model is already trained. It's actually going to apply the model and try to give the particular classification. So this is what, and this has predominantly many applications. For example, handwritten recognition, classifying. You want to actually classify whether it's A, B, C, D, E, you can do. You can do it for image classification. So all these kinds of, or if you want, you can even apply for even surveillance kind of a thing, where you want to know like who is a genuine person, who's not a genuine person. CNN has this great effect. So CNN is predominantly used for any kind of image classification problem action. Okay. The next type of deep learning is recurrent neural network. So far, the neural network we have seen are things that does not have any kind of memory cells. What do I mean by that? See, a typical neural network, let it be CNN or your deep artificial, you give the input, it processes the input here, it gives the output, it goes to the next neurons in the hidden layer, and it produces the output. But these hidden layers or thing does not have a memory cell that it remembers the past values actually. It does not remember that. Whereas a recurrent neural is something that can handle sequential data, wherein it will take the current input and also take the output of the previous input. That is what the recurrent neural means. It recurs actually. It actually memorizes the previous input because of the internal memory cells that they have. So it is a typical representation of a recurrent neural, where if you see the hidden layer, it actually keeps on recurring action. So what happens in a recurrent neural is something like this. So if you look at it, the t minus 1 and t plus 1 are the successor, and there is a state before this one and the state after this one. So what happens here is, if you look at it, you're having what is called the weight matrices actually, like a B, C, and D. So at this level, what it does is, in a normal neural, what will you do? You will just multiply the weights of the input and the weights connected to the hidden and get the output. That's all. Whereas here, it will apply the weight of this x of t, which is b into x of t, let us say, plus the output of the previous state, which is that ht minus 1, that is the previous hidden state, which it still remembers. That value is also taken and does the computation to produce the output action. Okay, that is what is given as f of c, the function of h of t minus 1 comma x of t. That is the weight of the current input, which is x of t, plus the weight of the previous output from the previous state, x of t minus ht minus 1, plus the bias action. To make it even more better, it is given as sigma, which is actually can be hidden like can be ReLU or 10h, weight of x of t plus weight of ht minus 1, that is the output of the previous state actually is taken, that is actually remembered, plus the bias action. And output is as usual sigmoid or softmax. So you'll actually get what is called wy into h of t plus the bias action. So that is the novelty of recurrent. Again, this is actually used for any kind of a sequential data actually. So you can actually apply it for a lot of things like image captioning, image classification. See, image classification, you can apply CNN also. But here, there are things that you can apply is, for example, like this, if you look at this diagram, you can actually use like, this is called like, there are lots of variations in RNN, not like CNN or deep artificial neural network. It has things like one to many, many to many, many to one. One to many meaning I give one image, based on that, okay, it can actually recognize what the word is. Let's say I'm giving an image, let's say apple or something. From that, it can actually recognize whether it is an apple, mango. So that can be given as an output. Then other one is like many to many. For each and every image I'm giving, it will give an output. So let's say I'm giving here one thing, here one thing, here one thing. So image to text conversion, those things are possible. The other one is like you give many input and based on that, it will give one single output. So there won't be any output here. So here, 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 finally, I'll get one output here only. Probably based on the image, you'll give one thing called like it's an apple or something. So like handwritten recognition. So lots of image-based NLP, wherein you want to actually do natural language processing, RNN is predominantly used. So a variant of RNN where it avoids any kind of vanishing gradient problem is LST, long short-term memory. LSTM is a special type of an RNN wherein it learns from what is called long-term dependencies. This is a special type of an RNN. This can handle image type of data, handwritten recognition, even natural language processing can do. But most importantly, this is one type of a neural network where it can handle things related to time series forecasting. Anything related to forecasting, I think this is one thing where it actually, because of its memory cell thing, even ANN also has been used, no doubt about it. But still, I prefer LSTM. LSTM has actually been brought predominantly for this because of the concept of this memory cell. So prediction and forecasting will have a better effect compared to the traditional neural networks. So here, if you look at it, again, same like the RNN model only, it has xt minus 1, x of t and xt plus 1 with the different hidden layers. So it is actually a repeated chain of neural network, wherein it is actually built with two types of activation. One is standards and the sigmoid layer. So you have the different things here called the forget gate, the cell state, and the output. So they actually follow through different levels actually by certain procedures. So what it does is, the first thing is you have to make a decision on the remembrance of the past data. What we mean by that is, we got to make you understand that here, based on the input that you are getting, what amount of information I have to remember which are relevant, that will be forwarded, that will be processed and forwarded to the next layer. That is what is the first step in the LSD. Because you don't have to forward all the data which is coming. That is not going to happen. The one which are relevant alone will be actually remembered, processed, and forwarded to the next level actually. So that gate is what is called as a forget gate, meaning the gate that actually forgets the irrelevant data, only remembers which are relevant and pass it on to the next state actually. So the first thing that it does is eliminating some of the irrelevant data. Irrelevant meaning, let us say like I'm going to actually do some prediction of sales forecasting. So I would require information about the year, the sales of the previous years and things. I don't require information about the customer's name or anything. I'm least bothered about it. So such kind of information or thing, I can actually remove it. Meaning I can just forget it actually. That is done at the first step actually. And this is actually done by applying what is called the sigmoid activation function will be applying. So it will be like weight of that into ht minus 1 plus weight of that into x of t plus the bias. By applying the sigmoid, you will make a decision which of the data are relevant, which of the data are not relevant. Only those relevant data you will take it. The rest of the thing you will just forget it and you will actually forward it to the next step. So like this. So you actually take what is, it is taking what is called ht minus 1 x of t. So whatever you are going to process here, it will actually see which of the data are relevant, what are the things which I have to remember. Only those things I'll remember and actually forward it. Same thing will happen here also. Which of the thing which is important, those things will be remembered, remaining thing will be dropped off, and the others will actually go to the next step. That is the first step actually you do based on the input that you get. That is the input is actually the xt minus 1. Based on the input, actually you are actually doing it actually. Okay, that is the first step. Right? What is the value that is acting as an input gate? The sigmoid layer is the one that is acting as your input gate. Okay, which is what is making a decision which of the contents of the memory I have to remember and process for, and which are the things that are irrelevant that will be knocked off. Okay, so where f of t, that's called the forget gate, and which decides the information to be left and information to be remembered and processed and sent to the next state. Next thing is selective set. Now that you know which of the data I have to remember, which of the data I have to knock off, or I'm not going to actually process and move it forward. The next thing is selective cell update values. So here what they do is, based on the decision on the size of the memory of the previous state, now a comparison is actually going to be made between the current input x of t and the previous output ht minus 1. That is the second step. You're going to make a comparison between the values between x of t and ht minus 1. That is the output of the previous step. So here you are actually going to determine how much of the past input is actually going to be included in the present input to be processed and forwarded to the next level, that is the output gate. Okay. So here a new vector candidate called CT bar is actually created, where you'll be applying tanh. Why you're not applying a sigmoid is because sigmoid is actually going to apply only in the forget gate. That is in order to help you act as an input gate for making a decision which contents of the memory cell has to be forwarded actually. That is the reason we apply sigmoid layer in the forget gate, because it acts as an input which of the contents has to be processed forward. That is why it actually helps in eliminating some of the irrelevant data. Okay, some of the irrelevant data will be eliminated based on the input that is coming from the input gate, where sigmoid acts as an input gate action. Okay, that is the major step. That is removing the irrelevant data and only capturing the relevant data, and obviously forwarding to the next step. Here a comparison actually made between x of t, because that is now going to have only relevant data, because all the irrelevant data will be removed by this sigmoid layer. Already is done. Once it is done, comparison made between this relevant data sitting in x of t and the output of the previous state, which is ht minus 1. That will actually make the LSTM to determine how much of this past input has to proceed to we include the present input. So a new candidate vector CT is created where tan h layer is actually applied. So that is what it is. Tan h says WC ht minus 1 and x of t, which is bias you calculate. Then the cell state is actually updated by taking the input from the forget gate, which is based on the input that actually going to take the relevant data that it actually has remembered in the CT minus 1, okay, plus I of t into C of t. So that is exactly what you have done here. So if you look at here, you have the CT minus 1 here. So that is actually, that is a cell state actually, that is the. So here actually it helps in deciding which of the information can be forwarded on the basis of the present timestamp. Then the last one here is, once it is cell state updated, now it is like which part of the present state can proceed to the output state. So here again, the sigmoid layer is actually executed to determine which are the components of the cell that are actually going to go to the output. Tan h also is applied here. This is just to limit the values between minus 1 and plus 1. Okay. So what happens here is the output value is given as sigmoid into, because that is the one that is actually going to determine which of the components of the cell is going to proceed to the output. So ht minus 1 xt plus the bias. Okay. Then h of t equal to ot into tan h of c2. Why we are applying this is because just to limit the value, just to limit the values between minus 1 and plus 1, we are just applying tan h into c of t multiplying by the o of t actually. So that is what is actually done. Okay, so that is what how an LSTM. First thing, deciding which of the input value you are going to remember and which of the data are relevant, which are irrelevant, that has to be dropped out. The sigmoid acts as an input gate, which makes a decision which contents of the memory to be forwarded. So that acts as an input gate actually, which of the thing has to be forwarded. So that's where the forget gate plays its major role. So the next thing is you'll make a comparison between the x of t value, there is an input value, and the previous output value, where a new vector candidate is created like C of t, where you apply the tan h value to write the memory cell. So that based on that, the C of t cell state is actually updated by multiplying the relevant value, which is wherein the irrelevant value which was actually created, if you know, the forget gate which was actually computed by applying the sigmoid layer, where that is your input gate. So remember only the relevant information and irrelevant information will dropped off into the CT minus 1, this is the previous state, plus I of t into the CT, that is the vector. So once you have done that, now the final part will be which are the present state that you have there, the xt, ht and ot value, which are the thing is actually going to go to the output. Here the sigmoid layer again is actually applied, which are the memory is going to be written. For writing into the memory, I think you apply sigmoid layer only. So actually you apply. So you apply that and get the value. But in order to limit the output of the hidden layer, that h of t, between what is called minus 1 to plus 1, you just apply the tan h on the cell state. So this is how LSTM actually works. Very much used for NLP, image, then time series forecasting and things like that. So this actually ends about all the machine learning and deep learning frameworks I have said. Then a little bit glimpse about what agents are. So agents again are another subset of artificial intelligence, wherein this agent actually can be embedded with what is called this machine learning and deep learning. So agents is something wherein it is again like a software program which can actually move from one state to the other to perform its job actually. So a traditional agent, this agent also was devised way back in 90s by Edzoni and Well, and each one gives a very different definitions about the agents actually. So agents actually range from a lot of purpose. For any kind of automation or thing, obviously agents can be used. So they actually perceive this as a sensory information where you get the data and then you apply the knowledge representation like your AI techniques and things. And based on that, the agents can actually behave. So agents growth actually goes, initially there was RPC, then they came was the remote evaluation, then was agent, wherein it does not behave on client server. The agents actually move with the code data and context of the place where the processing is done. From there, it keeps migrating to the different nodes to do the job. So typical properties of an agent, if you look, first it has to be autonomous agent, meaning it has to perform its task without the need of the human. So that means there's a need of artificial intelligence algorithm that has to be there, or any kind of a decision processing algorithms. Actually. Social ability, meaning the agent should interact among themselves to perform the job. Then proactiveness, meaning the agent should actually act upon its own without the need of any kind of a human intervention, and it has to be very responsive. Then what is this intelligent agent? An intelligent agent is something is going to have all the features that an agent has. Along with that, they also have some level of intelligence, which is actually going to come from these kinds of artificial intelligence, like machine learning, deep learning, to perform its job. So the main classification we actually say about agents are, one is static, whether the agent does not move from its place. It actually sits and constructs what is called a multi-agent system, where each of the agent can talk among themselves to get the job done. Mobile agent is something where the agent actually moves along with the code, data, and context from one node to the other, along with this kind of machine learning and AI algorithm embedded, or any kind of fuzzy-based algorithm to perform the job. So why we need intelligent agent is similar like AI. With the growing complexity of systems and the advent of IoT and thing, there is a need of automation. See, AI and thing actually, yes, they give the prediction classification, but if you want to actually automate the job, you also have to bring in another subset of AI, which is agent integrated with the machine learning or deep learning. Only then the automation can actually happen. So that is what is my way of looking at it. So AI and ML, yes, it does the prediction classification, but if you want to bring in some automation along with agents, this ML and deep learning has to be integrated. So the complete system will actually behave in an autonomous fashion action. So finally, touching upon big data before I go to the case studies. Now the data which is generated by the IoT, where you're actually going to perform the intelligent analysis and thing, and you're going to give the prediction with the advent of agent for computing and thing. The data which is generated is our voluminous. It's not very small data. It's a huge amounts of data you're going to get generated. And how to actually store this large quantity of data? There are 4 V's they actually, for now they're going to 5 V's also, like volume, variety, velocity, and veracity. So these data that we get are structured, not structured, unstructured. So we saw like CNN or images. Then you have like NLP. Then you have like images. Then you have like speech. These things are non-linear data, non-structured data actually. So how we are actually going to store this data? The traditional database actually have things like, float, double, and things. But these things you cannot keep on creating different data formats. So that's why they actually brought what is called NoSQL database. And there are things like Cloudera, MapR, and things where you actually store the data. So this is the complete Hadoop ecosystem in your cloud, how the data is actually going to be managed and stored. So there are things like, MapReduce that is responsible for, this is the Hadoop work system, they say, like HDFS, they say like Hadoop distributed file system, where they actually say how exactly the data is actually going to be stored in the form of a file system. So then there are something called MapReduce that actually is how you can optimize the load in the cloud and things like that. Then there's something called Hive that is actually due for any kind of SQL kind of a query. Then you have Uzi that is actually for workflow management, and Zookeeper. So that's a complete Hadoop ecosystem, which are the very important tools that are actually used for managing, storing your data in your big data environment. Now, the thing that I'm going to say before I step into okay, இப்போ நான் வைண்ட் அப் பண்ணமா இப்படி ஓ அப்படியா என்ன நம்ம கொஞ்சம் அப்படியா ஒரு 1:30 வரைக்கும் வச்சுக்கலாமா பண்ண முடியுமா அப்படியா ஓ ஏன்னா நம்ம ஆரம்பிச்சது கொஞ்சம் லேட்டா தான் ஆரம்பிச்சோம் நம்ம ஏன்னா என்னதுக்கு ஒண்ணு நான் பண்ணிடுறேன் என்ன ஒரு 10 நிமிஷம் இந்த IoT சொல்லிட்டு ஒரே ஒரு கேஸ் ஸ்டடி சொல்லிட்டு வைண்ட் அப் பண்ணிடுறேன் நான் ஓகே ஒரு கேஸ் ஸ்டடி நானே சொல்லிடுறேன் ஓகே Okay, I just got a call like we're running out of time because there's another session. So what I'll do, I just say this and just I show you only one case study about like the IoT AI edge with the energy sector, and then I'll just wind up actually. Okay. Okay. So the final thing that we are going to say here is with IoT being talked, AI being talked, edge also being talked. So there is a need of an integration because as I said, edge is where all the processing and things are actually going to happen. And that is where almost all your processing going to happen because of the latency reduction and reduction in the cloud workload and things like that. So we are actually pushing all the intelligence at the edge level actually. So all your analytical model and everything are actually going to be deployed there with agents, machine learning and deep learning, and analysis is actually going to be taken and quick decisions actually can happen. And the macro level data analysis are actually going to happen. So that is the latest trend where the research is actually moving forward. So with this as a basis, there has been some work which has actually been done by my research group because I started a bit late because of my official work. So I'm not able to go through all the case study. One of the case study I'm going to talk about is actually like, which is quite interesting, is a fog-based power distribution where we actually proposed a power distribution system for a consumer side. So what exactly this work actually does is, if you look at this diagram here, we have an edge-based system here, a fog, where I have my analytical model. And that model actually does two things. One is forecasting about the energy required for the consumers. Okay. So we had a data set which was actually like about, the data set we had was about like a 1 crore data sets actually. So that one was actually taken and we applied the time series model. And based on the time series model and thing, obviously the forecasting is actually done. And we actually took the data for 20 residential house for 2 years, and we developed the model. And that model would stay in the form that will keep forecasting how much amount of energy is needed, not for a long term, for a shorter term, that is for the next 72 hours, because the data we got was like every 8-second data. So we had such amount of data that we got, that is from UK, that is RFID project. Now, based on that, the next thing we actually did was, these are certain models like how we actually did it. This thing is available in my paper. If you can look, it's published in IEEE IoT journal. You put my name, you can get this paper to get more details. We do the prediction. Then we actually went to what is called demand reduction. So most of the time, utilities say try to reduce the demand, try to reduce, but none of us actually do it. So here we are coming up with a policy wherein we can actually try to see which of the appliances are playing a dominant role during peak and non-peak hour. So we brought what is called a statistical analysis, where the data set also had the power consumption of each and every appliances actually. Okay, each and every appliance's power consumption was also there for the four. So we took a period, November to February, that's a winter time in the United Kingdom. So accordingly, we what we did was we normalized the number of times appliances are used during that period. Then we applied what is called a discriminant analysis. And based on the discriminant analysis, we get a structure matrix which actually ranks which of the appliances play a dominant role during the peak and the non-peak hour. So this is the model that will be actually sitting inside the fog, and then the forecasting model that will keep on doing for one particular season on a daily basis, which of the appliances are playing the dominant role during peak and non-peak. And accordingly, actually, the agent actually here would play its part in actually doing the demand reduction. How it is actually going to be done is actually shown in the next diagram. So here what happens is we have various agents actually deployed. As I said, here my forecasting as well as my demand reduction model is actually sitting, wherein this is actually going to focus how much of power is actually needed for the next 72 hours. So I know the consumption pattern. Plus, actually, I have what is called the structure matrix, which says like for that particular season, which equipments are playing a dominant role in peak and non-peak hour. Now, my agent in the cloud, that is my utility, is actually going to interact with the user, asking whether he'll be willing to participate in the demand response program. Based on that, what happens is the agent here in the form will negotiate with the meter agent for the demand reduction. So it will ask which of the equipments you want to actually be applied to the demand response. Meaning, you can actually shift certain equipments during the non-peak hours. That is the time where the demand is low and where the renewable energy is in surplus. So based on his actually selection, what will happen is the fog agent here will actually, the negotiating agent will actually send a proposal from the meter agent by how much you can actually curtail the load during the peak hour. So it will look into the proposal and say which of the proposal is actually acceptable. And then that message will be sent to the utility. That is your electrical department. That electrical department, during that time, he will automatically control the equipments that you are using. That will, it will control the load that you are actually using at your home. During the non-peak hour, the equipments which are not used in the peak hours, let's say you're not going to use your washing machine thing, those things will actually be shifted during that time. So this way, the ultimate, this was actually done using paid, which is called an agent development environment. And accordingly, what you see here is based on the day ahead prediction, the predicted demand is this one. And during after negotiation, into non-peak, you can actually apply some of the equipments during use, because this is the time where you have renewable energy. So there will be a reduction in the bills and thing. And this is the time where you peak. So there, if you can see, your predicted demand is more. Based on the negotiation, I have curtailed the load. That is the demand. So this is the curve actually that shows it. Okay. So there are lots of other things. So those things are actually published. I'm not having time to actually cover it up. There's one last one I want to show, which is actually quite of an interesting thing that you can. Okay, the IoT edge intelligence. So the last one work which we did actually with my PhD candidate was when we talk about edge AI and IoT integration, we came up with actually, because there is no proper model which actually says how the data has to flow, how the data is actually going to be modeled. When the data comes in, we say like, yeah, at the edge, we have an analytical model to perform the job. But how exactly the data is actually going to be streamed, how the data actually has to be flown, how the data will be processed, those things are not talked about. So we actually here focused on data flow and a distributed deep learning in the IoT edge to bring down the latency. So here we actually propose architecture wherein if you look at it, these are my IoT devices, the sensors and actuators. Here we have the edge devices where I have the big data tool called Mini-NIFI that is responsible for capturing the data that's coming to the edge and aggregated by what is called the Kafka program. Then from that, actually it flows to queues. It is actually queued and is actually taken by the streaming analytics manager where all the data analytics is actually done. And then it actually proceeds to the cloud. So the proper data flow model with the deep neural network, the deep learning framework actually was proposed here. So based on that, what happens is the distributed deep learning does not happen only at the analytical level. It actually starts from the phase where the data is actually collected, that is at the edge layer, where it actually makes a prediction. What is the kind of event actually has to be fired? Based on the event, what kind of an action has to be taken, that the deep learning. So the deep learning is actually going to be distributed across the different layers in the fog actually. So first at the edge layer, where it will actually make a prediction of the event. Then at the edge server, it's actually going to make a prediction what kind of an action has to happen for that kind of an event. And then at the finally the cloud layer, where you're going to do the big data level analysis. Okay, again, this is also published in Engineering Applications of AI. So if you put my name, the scholar page, you'll get all the details. You can download it. So here, finally, what we proved was when we compared the latency with the distributed deep learning, distributed across the edge, and when compared it with the cloud, we found that the latency in terms of network service and the total latency, we have actually reduced it by 33% actually. 33% reduction was actually achieved as compared to the traditional workload. So the thing that you're going to take away from my talk, if you look at it, see, IoT edge AI integration is the latest field that we are talking about. Today's industry 4.0, 5.0 is actually talking about automation, where there is a need of what is called AI and has to be developed in all the edge gateway. Lots of industries are coming from edge gateway, where these kind of AI applications actually can be written. But there are some challenges that we have in front before these kinds of integration can actually happen. First of all, there needs to be standardization in the IoT communication because we have different objects coming up. Then is the intelligence that we talked about. There is a new wave that is actually being talked called like explainable AI, because the machine learning or deep learning, it's like a black box. Inside, there are lots of things that are actually happening, but you necessarily don't know what is happening. So how you can actually rely whether the model that you have built is reliable and can be adapted to the industry. So like her healthcare applications. So explainable AI goes in depth into actually explaining in a human readable format, like what exactly is happening at each and every level, at each and every hidden layers of the neurons. So that is something really coming up, and there are lots of models that is actually being used, like Lime and Deep Lift actually. Finally, is the security. With the data being distributed across the edge and thing, security is a very big concern that has to be looked into. The big security protocol like AES, MD5, I think cannot be applied for this kind of resource constraint. So there has to be some modification and research work that has to go into modifying these protocols for edge without compromising security. And blockchain is also another area. So that has to be integrated with this kind of deep learning for actually managing the security. So thank you very much. So in this talk, I'm sure you would have learned a lot, like what IoT, AI, edge and thing. And there are lots of work that is actually out there. A lot of work and projects can be done. So I couldn't have time to actually talk about the various case studies, unfortunately, because of time constraint. But these works are actually available on my Scholar page for Google as well as the Scopus. You can actually download it and publish in higher journals. And you can actually get a good understanding of what kind of work we have done in our university. Okay. Thank you very much. Oh, someone wants my PPT. Okay. Okay. This, you want to know which software is used for implementing agent concepts. Okay. Agent concepts you can. Okay, this answer. Which concepts? Okay, the concepts which we actually use for implementing agents are like one is actually is like paid. We actually use that is for the energy thing. There is something called net logo that you can use it, and then there is something called spade, which is actually in Python. You can use it. There were things that were used previously like Jade and things, but that's all Java environment actually. Okay, the PPT I will share it with Mr. Jagadish, and he will actually send it to you. Okay. Any more questions or any kind of thing you want to know?